This is 39. We're looking at lines of symmetry. You've already been working with lines of symmetry when you were doing your transformations, when you did reflections. So looking at, you don't have to open your booklet, but looking at your booklet, look up here. There's no line of symmetry in a translation because the shape is just shifting over, right? If I was to fold this picture in half, the triangles don't match up because they're facing the same way. So if I fold it, they would not line up. But if you look at with a reflection, this line of symmetry, which is the x-axis in this example, if I fold the picture along the x-axis, meaning that the x-axis would be the crease in the paper, if I was to fold this, my purple image would match on top of the black pre-image, right? That means this is symmetrical. What is it symmetrical to? What's the line of symmetry? In this case, it's the x-axis, because that's where you would fold it for those to match. The line of symmetry here would be the y-axis. That's where I would fold it, and those would match. You even can have lines of symmetry with Hoy-Bucks. So this is when it's kind of off-center, but then you just need that equation of the line. Hoy-Bucks would help you to remember. Most people got this right on the quiz. There was just a few people who had it switched. Remember, Hoy-Bucks is telling you if it's y equals a number, then it's a horizontal line, crossing the y-axis at that number. If it's x equals a number, then it's a vertical line crossing the x-axis at that number. So where's the line of symmetry here? Well, where would I fold the picture for the image to match? If it was not already highlighted and you were trying to find it, what you would do is just take 2 points that match, like A and A prime, and just find the distance between them, and whatever's in the middle is your line of symmetry. So it's 1, 2, 3, 4, 5, 6 spaces apart, so then the middle would be 3 spaces in. Does that make sense? That's another way to find the line of symmetry if you have trouble visualizing where would I fold it. Just find 2 points that correspond and just get the middle. Okay? Line of symmetry here this is the only diagonal reflection that we cover. This is the only one. Reflecting over the line y equals x. Rotations don't have lines of symmetry, but they do have what's called rotational symmetry, which is what we're getting into. So coming back to this. Okay, we've got a couple of types of lines of symmetry, and we're going to highlight as we go. The first is a vertical line of symmetry. Vertical line of symmetry means that you can fold the image. I gotta open the door, the heat's killing me. You can fold the image, what is it called, hot dog style? Because the paper's long, so it'd be hot dog style, where it has a vertical crease in the paper. For instance, if you look at the graphic here, if I had a paper with a capital M on it, I could fold it right in the middle, and there would be a vertical line of symmetry, right? Horizontal line of symmetry traditionally is called folding it hamburger style. That's where you're folding the paper down or up, and it has a horizontal fold in it, crease, and that would be the horizontal line of symmetry. Notice that if I took a capital H and I folded it right in the middle, that it would be symmetrical. The bottom picture matches the top picture. Looks like a reflection, right? General line of symmetry, just a general, what happened? here yesterday. Try to get general line of symmetry means where could you fold it that's not horizontal or vertical, so it could be slanted. So if you look at this polygon here, we have 6 sides. Do you remember what a 6-sided polygon is called? The X in 6 is your clue. You got it? The X in the word 6 is your clue. I'm just curious. It's not like you should know this. Hexagon, yeah. The X in 6 and the X in hexagon, that's the only one with an X in it. That's how you remember a 6-sided figure. We have a 6-sided figure here. So I can do a vertical line of symmetry. I can do a horizontal line of symmetry. But there's other lines of symmetry here because it's a regular polygon, meaning all the sides are equal. I could fold it this way. I could fold it this way, or this way, or this way. And those are all different types of lines of symmetry. If I was to ask you how many lines of symmetry are there, when you first look at the picture, you might think there's a ton. But how many is there actually? How many lines is there? How many lines total? 6. 1, 2, 3, 4, 5, 6. It looks like there's a lot more, and that's because, you know, when you mark one line, it does have 2 ends to it. So, but there's 6 lines of symmetry. Why do you think there's 6 lines of symmetry? 6 sides. Those go hand in hand. So how many lines of symmetry do you think a square would have? 4. What about a equilateral triangle? Equilateral meaning all the sides are equal. 3. Pentagon? Who is it? Huh? 5. Pentagon in Washington, D.C. If you've ever seen the aerial image of the Pentagon, it is a regular pentagon. That's why it's called that. 5-sided. Okay, which brings us to a couple of new ones. We've got rotational symmetry. There's one type of rotational symmetry that is very specific, and it's when it can be rotated 180 degrees and it matches up. Rotational symmetry of 180 degrees has a buzzword. It's called a point symmetry. Point symmetry. So take your paper. Can I borrow yours since yours is out of your notebook? Now ignore the writing on the paper. Just pretend like you see a white rectangle, right? I'm holding it upright. And ignore the holes. Let's play the game right. So if I have this white rectangle and I was to hold my finger down in the middle and turn it 180 degrees, did it just land in the same shape as it started as? It's a white rectangle, right? In the same position. Now, granted, I did turn it upside down, but like if you're thinking of a shadow being projected on the wall, and then I rotated it 180 degrees, it would be the same shadow. See what I mean? So that's a symmetry. It's a rotational symmetry because I turned it 180. It's called point symmetry. Okay? Don't let the 180 throw you off. All it means is turn it upside down. Okay? Turn it upside down. Is it the same thing? So if I had a heart, just a classic heart, and I turn it upside down, would it have point symmetry? No, because if I take a heart and I turn it upside down, I can't turn my arms, y'all, so I'm going to do a reflection instead. But my arm, imagine my arms turning, right? Okay, it would land upside down, so it does not have point symmetry because after I turned it, I now have it, it's in a totally different position. Does that make sense? Just pinch paper, sorry. Okay, so that's point symmetry. You take capital N and you turn it upside down. Everybody turn your notebook upside down. Watch that N. Watch the capital N on your paper. Turn your notebook upside down. Do you notice that it is still a capital N? That's why it has point symmetry. Okay? Which brings us to, what if it has other types of symmetry that's not necessarily 180? That's just called rotational symmetry, and the way you find it has to do with the number of sides. Alright, so let's see if we can get there without me just throwing it at you. Let's work with a shape that's easy for everyone to understand. And you don't have to write this. I'm trying to get you there. If I have a square, right, does it have point symmetry of 180 degrees? Yeah, because I could definitely turn that upside down and it would be the exact same image as it started as, right? So it definitely has 180 degrees point symmetry. Does it have any other types of degrees of symmetry? What's the one obvious one that every single shape has? What do you think? It's boring. It's got 360. Every single shape has 360 degrees of rotational symmetry, because that would mean the shape rotated all the way around and landed right back where it started from, right? So yes, it has 360 degrees of rotational symmetry, but every shape does, so we're going to call that like a moot point. We don't care about it because every shape has that. Is there another type of symmetry? Can you think of how many degrees could I pick this up and turn it and it would land right back as a square? Like that. I may need to draw a square because I don't think I can rotate that. There we go. There's a square, right? How many degrees is that? Watch where my pen went from. I went from this top left corner to the bottom left corner. How many degrees do you think that is? What? 90. How many degrees do you think this is? 180. How many degrees do you think this is? 270. And then now notice I'm right back where I started. How many degrees is that? 360. So we said 90, 180, 270, 360. How many degrees of rotational symmetry did we end up having? 4. How many sides did it have? 4. Could I have gotten this list of numbers without sitting here playing with the picture? What do you think I could have done? I could have looked at the sides. How many do you have? 4. We're going to say N represents the number of sides of the shape. In this case, we had 4. How many degrees is in a full rotation? 360. What could I have done? There it is. I could have taken the full rotation that every shape has, and I can divide by the number of sides that are equal. And it will give me, in this case, I would have had 360 divided by 4. I get 90. It's going to give me the increments of my rotational symmetry. I can rotate 90. How do I get here? From 90. Can I see it? I can rotate 90. Where do you think the 180 came from? Add another 90. I got 180. Where did this come from? Add another 90. I got 270. Where does this come from? Add another 90. I got my checkpoint 360, which lets me know I did it correctly. All right. Now, if you're not quite understanding, let's try it again. with a triangle. We've got an equilateral triangle. What do you think is the smallest degree of rotational symmetry? How would I find it? I take the full rotation divided by the number of equal sides. 360 divided by 3. Do 36 divided by 3 out of 0. What do you get? 120? Yep. So, let's talk about the degrees of rotation for a triangle. You got 120. What's the next one? 240. And how did you get that? You add another 120 to it. It's increments of 120. So I got 240. What's next? 360. Which is my checkpoint, which is my move point. We said it's boring, but it's a checkpoint to let you know, yeah, you did it right. Okay? Alright, so now what do you need to put on your notes? So come down here. What shape is that? That, how many sides? Keep going. That's a hexagon. So how many sides do we have? We have 6 sides. N stands for number of sides. There's 6 sides. Don't holler out. Everybody write down on your paper. Tell me the degrees of rotational symmetry of a hexagon. You're going to go through the same steps that we did right here. I'll come over here and bring it back. I'm trying to find it. Hold on. There it is. Tell me the degrees of a hexagon. The rotational degrees of a hexagon. How do we get there? What? And how did you get the 60? You're right. Oh. Do you know that I've not noticed that ever? How would we get the 60? Why is 60 important? Where does the 60 come from? So the formula, the little formula is you're going to take, I guess I'll write the formula up here. The formula for rotational symmetry is 360 divided by n, which represents, we're going to write the word sides, represents the number of congruent sides. In this case, we have 6 congruent sides, so 360 divided by 6 is 60. So this hexagon has a rotational symmetry of 60-degree increments. So if I was to say, can you list them, you would start at 60, and how do I get the next numbers? You keep adding 60 until you hit what checkpoint? Until you hit 360 to let yourself know, yeah, I did it right. So there's 60, what's next? 120, 180, 240, 300, and 360. I'm always going to write it, and I'm always going to strike it out and put a check mark like, yep, checkpoint, I did it right, but 360 is forward. I love rotational symmetry because it's really not that bad, but it sounds so sophisticated. You know, like you look at a shape and you're like, ooh, this has 60-degree rotational symmetry, and people are going to think, man, you're a genius. How did you pick up on that? And it's like, it's simple. It has 6 sides, right? All right, let's come over here and practice. We're going to practice with capital letters of the alphabet because lowercase letters are not as interesting. I am going to write the alphabet with capital letters at the top of my screen so that we can use the same font, right? Y'all know the fonts on computers. Some of them are a little crazy. So like A. Now assume assume these are perfect, please. If you write your B like this, there's no symmetry to it. But if you write it like this, would you say there's a symmetry? I could fold that horizontally. I could fold it down and it would match. So we're going to argue that B can be written with a symmetry. You got the same thing with C. C's kind of one of those. All right, take a second. I would love for you to answer questions 1 through 6 on this paper. Now, 1 through 5 is talking about letters of the alphabet. Number 6 is going back to that rotational symmetry. Everybody try right now. So we're looking at what letters could be folded hot dog style. So they're upright and then you just fold left to right and it would match. Somebody want to say a letter? M? Someone else? W? Maybe not when you write it the way I just did, but yeah. Did someone say V? Yep, V. Anyone else? A? H? I? O? Yep, T works. X? And Y. I didn't find any more. Those are the ones I found. If you came up with 2 letters that's in that list, then you did it right. The restriction was that it had to be able to fold from left to right, right in the middle of the letter, and match. All right, the next one is horizontal. This is hamburger style, so like folding the top down to the bottom and it matches. What'd you get? B. If you write B, like we said, then you could argue it folds and has that horizontal line of symmetry. Anyone else? If you write C kind of like a circle that just didn't finish, I would say that it folds. Now, if you do your C like this, then it doesn't fold. So C might be a tricky one. I heard another one. What was it? H. Definitely folds. I folds. D, I would argue D folds. E folds. O. This just keeps getting in the way. What else? X. And then I said one more. I don't know. Might argue this one. I guess it depends on how you write your K. If you write a K like that, or I don't know. Anyways, I don't know how many ways there are to write one, but I would say if you write the K in a way to try to be symmetrical, like you could fold that down and it would match. What letters have both horizontal and vertical? O, X, I, and H. What letter can you rotate upside down and it matches, but you cannot fold it hot dog style to match? S. If you draw an S on your paper, look at it, turn your paper upside down, is it still the correct S? Yes. Now go back to the S. Can I fold the S from left to right to match? No. So that definitely works. I think there's one more. N we know has the rotational symmetry for sure. We already know that. It was on the front. And if I fold it from left to right, it will not match, so N works. Does Z work? If I take Z, I don't even have Z. Oh, now I know why. If I take Z and I turn it upside down, is it still a Z?
No.
Wait a minute. Yeah, it's still a Z, right? I know. Gotta really get into it. Can I fold Z from left to right and it match? No, that diagonal is the problem. So I would say Z works. Is there another? I don't think there is. I think that might be it. What letter, depending on how you write it, could have infinite lines of symmetry? Everybody should have been able to come up with the fact that O has infinite lines of symmetry, as long as you're not writing it as an oval, right? If you wrote it as an oval, then it doesn't work. All right, come down here. You were supposed to draw the lines of symmetry. What shape are we assuming that this first one is? Square. What about that one? Triangle. We're going to assume it's in, do you remember the vocab word? Equilateral triangle. We're assuming that all the sides are equal. There is a vocab word right here. It says regular shapes. I need you to know that this means all sides congruent. It means all angles congruent. When you are told you have a regular shape in front of you, it's kind of sneaky. It sounds like a word just saying, oh yeah, I've got a regular shape right here. But it actually is implying, hey, all the sides are equal, all the angles are equal. There's a lot of information in the word regular. How many lines of symmetry did you draw for the square? Okay. If you drew 2, I'm going to challenge you to look and draw 2 more. If you drew 3, find 1 more. How many lines should there be total? 4, because how many sides are there? 4. You might be wondering, like, where are the 4 coming from? You probably nailed the vertical and the horizontal. But could I also fold it diagonally and this image match over there? Yeah. Yep. And what about this way? So there's 4 lines of symmetry. I would love for you to tell me the rotational symmetry right here. Tell me the degrees of rotational symmetry. Now we did this on the other side. You need a refresher. What are the degrees of rotational symmetry for that square? What's the smallest degree of rotational symmetry? 90. And how do we get the 90? There's 4 sides. We're going to do 360 divided by 4, and that gives us the 90, which is our starting point for rotational symmetry. So there's 90. How do I get the next number? Yeah, whatever you've got here, you now add it in increments to itself, to the last number. So next would be 180, and then what? 270, and then your checkpoint 360, which we mark out because every shape has 360. But we do get there just to kind of be like, yep, I did it right. How many lines of symmetry should this equilateral triangle have? There should be 3. You might have found this one, and you might have said that's all there is. But that's because your mind is stuck with the triangle upright. I want you to take your paper, turn your paper so that the triangle is upright, but on another side. So like if you are looking up here, because I can't turn my image, if I take some, right now, this is my base, right, the bottom. I want you to take your paper and turn it to where this is the base. Do you see this line of symmetry now? You see that? Is there another one? Yep. The side we haven't done yet, if you take your paper and turn it so that this is the base, you probably then see that line of symmetry. Oh, I did not hit that correctly. I should have gone right through the corner. But there's 3 lines of symmetry here. All right, let's find the rotational symmetry. Of an equilateral triangle. What would I do? 360 divided by 3. What do you get? 120. So it's 120, 240, 360, checkpoint, and mark it out. Go to number 7, says, what are 3 transformations that would map this onto itself? When it says map, mapping means you move the shape, but then it lands right back in the same shadow as where it started. Okay? It doesn't mean point A lands back on point A necessarily. It means the overall imprint, the shadow, think of it as a shadow. You pick the shape up, you turn it, and then it lands right back in that same shadow. What type of rotation could we do to land it right back on itself? You could do a 180. If you look at your paper and you turn your paper upside down, does it land back in the same shadow imprint? Yes. So 180 definitely works. How many sides do you see? 6. Can we get some more? We could rotate every 60 degrees. Where did the 60 come from? We could do 360 divided by 6 to get our 60-degree rotational symmetry. So we could rotate 60. What would be next? 120. Next, 180, and then next, 240, then 300, and then 360. Check. Work it out. Now let's go back to stuff we learned earlier in the week. Is there a reflection? Is there a reflection where you could take the image and you could flip it and it would land back in that shadow? Over the what? Over the x-axis? Could I take it? Imagine if I was able to spin, like not rotate, spin, I shouldn't say spin, flip. Imagine if the x-axis was like a bar, an axis of symmetry, and I was able to take this shape and reflect it. Would it land right back in the same imprint? Yes. So you could reflect over the x-axis. Is there another reflection? You could reflect over the y-axis. Imagine the y-axis is an axis of symmetry. If I could take the shape and reflect it, flip it over, it would land right back. Now, keeping all of that in mind, look at the next one. The next one is a trick question. Is that a rectangle? No, it's not a rectangle. It's a what? That's a parallelogram, which means it's a rectangle. Here we go again. That's been pushed, right? So it's like oblong, meaning like it's not perfectly upright, it's oblong. So can I flip that over the x-axis to match? Wouldn't work, would it? If I flipped over the x-axis, this point would land here. Is that the same shadow imprint? Not the same. Can I go over the y-axis? If I go over the y-axis, this point would land here. Is that the same shadow imprint? No. There is one type of move you could do. Can you look at it and figure it out? Or look at your paper and play around with it? There's one move you can do. What? 270. Think of 270 as 390s. So there it is. So if I have a let's play with a rectangle for a second. If I have a rectangle and I rotate 90, my rectangle is now in a different orientation, right? But if I have a rectangle and I rotate 180, I'm still back in the same orientation. Take your paper, look at that parallelogram, and turn it upside down. Is it the same shadow imprint? Yes. So a rotation of 180 degrees. I didn't mean to leave this in red, but we'll go with it. You could rotate 180 around the origin, and it would land back in its original position. Now, here's why this is one of my favorite lessons. Look at the bottom of your paper. You may have probably ignored it because there's no math question. It's just a bunch of pictures. What is the what's the second word say? Algebra. What's the third word say? Mathematics. The first word says ambiogram. These are ambiograms. This is when math is in the real world. Tattoo artists make ambiograms. I want you to take your picture, take your paper, study those words. Ready? Wait for it. Now take your paper and turn it upside down. What do you notice? It is the exact same word, but you totally turned your paper upside down, right? So should it be the same word? No. Ambiogram. So tattoo artists, what they do is they use a certain font and a design with that font to make words, when you turn them upside down, be the same. And that's because nobody wants to get mom tattooed on their arm, but when they look at it, it says wow. See what I'm saying? Like, I don't want mom on my arm, and then I look at it and it says wow because I'm upside down. And I don't want it to say mom to me, but then everybody else looks at it and it says wow. Like, oh wow, you got a tattoo that says wow. Then, no man, it's mom. Oh, it's upside down. So an ambiogram is what tattoo artists use to try to make the tattoo read the same thing no matter if it's upside down, right side up. All right.